So what I want to do today is talk a little history, tell a war story or two, and then talk about some science. The topic will be NMR and this computational molecular modeling. Before we get going, I especially want to thank the U.S. National Science Foundation that supported our work early on, U.S. Department of Energy, Office of Science that supported us most recently. And I especially want to thank those folks there, Andrei Kalinichev and Randy Seigan, who introduced me to computational molecular modeling, really got me into this. It's been a terrific collaboration working with those folks over the years. And I want to thank Jeff Bowers and Ozgur Yazad, and Ozgur's here today. Much of the more recent work that I'm going to show is actually Jeff's work and Ozgur's work. So let's see. Make this go. There we go. So it's been my great pleasure over the career to work with an awful lot of really capable people. And I just want to make sure, I may have left somebody off, but I hope not. I want to thank everybody on this slide for all their contributions to the work that we've done over the years that would not have been possible without terrific collaborators, terrific postdocs, and terrific students. So NMR, the physical phenomenon of magnetic resonance, was discovered in the late 30s, and it was discovered in solids and liquids in 1946. Robbie, Bloch, and Purcell all got Nobel Prizes for their work. It was of interest mainly to physicists, measuring nuclear spins and things like that for many years. But in the early 1960s, commercial spectrometers became available, and it worked its way into chemistry. And the first applications to clays were actually very early in this system. And I've just mentioned a few papers there. There were many, many others. What happened in the late 1970s and early 80s were a number of technical developments that really changed the applicability of NMR. It really increased the applicability of NMR. And that includes high-field superconducting magnets. There's one of them there. This pulse Fourier transform method of data acquisition, magic angle spinning that many of you have heard about, multiple quantum techniques. And what that did was open up the periodic table to a great raft of nuclei. And it really, it changed the breadth of applications of NMR in all kinds of chemistry. And I always like to point out this paper by Enda Lippmann and his collaborators in 1980, Structural Studies of Silicates by Solid-State High-Resolution Silicon-29 NMR. Changed my life, and it changed a lot of other people's lives in understanding aluminosilicate materials. So where did I come in this? Well, it was a Saturday night. This is a true story. Saturday night, we had just finished dinner. A couple of the kids, and we were sitting around. Telephone rings, and pick it up. It's a guy named John Hauer, and those of you with gray hair will remember John. He was our department head at the time, my department head at the time, and also a leader in clay mineralogy. And Saturday night, John says, "Jim, I'm in the St. Louis airport, and I got to talk to you." And it turns out that he had been down visiting mobile oil labs with this fellow, Don Wiesner, right there, the author of that paper. And Don had talked to him about all these new techniques, high-field superconducting magnets, magic angle spinning, that stuff. And John was so excited that on his way back at the airport, he called me up and said, this is fantastic. I got to talk to you about it. So we talked for a while. I said, okay, John, I don't know how many beers he had had, a few probably. The next Wednesday, a student came by from the chemistry department in Illinois, and she said, I'm from Professor Oldfield's group. We have a contract to work on zeolites. People tell us you know about zeolites. Maybe. But this was a group of biophysical chemists, and I actually did know more about zeolites than they did, marginally. And that was Sue Schramm, who went on to do a lot of the oxygen, the early oxygen NMR work. And so John encouraged me to go talk to these people. So over that summer, I spent quite a bit of time with Eric Oldfield and the students, learned more and more about NMR, and I said, John's absolutely right. This is fantastic. This is all brand new. It's going to be very, very useful. So I called up my NSF program director. I had a grant at that time to actually measure crystal growth rates from lava. It was a different scientific direction. And I said, I'm going to change to this NMR. He says, okay, it's your career. So we did. And it's worked out very, very well. And I will say it's been fantastic being able to be involved early on in something like this. At that time, we were like children in a candy store. It was, much of the periodic table opened up to the kinds of work we were doing, and working with Oldfield's group and his students and postdocs was a terrific experience, and we got lots of work done. All right, so what's so special about NMR? Well, first off, it's element specific, which is quite different than most other spectroscopic methods, not all, but many others. It's element specific, and it can simultaneously probe molecular scale structure and dynamics. And this, to me, is its great power. It's this simultaneously looking at structure and dynamics. So we can get structure through the chemical shift, through the various quadrupole parameters, line shape analysis, and often related to the quadrupole parameters. Dynamics through various relaxation methods, T1, T2, line shape analysis. And for many of the data we're going to talk about today, that means that variable temperature experiments is very important. So just talk a little bit about dynamics. Here's a scale of 10 to the 14th range in frequency. Infrared spectroscopies and vibrational spectroscopies up there. NMR spectroscopy probes these relatively low frequency range. Typically, T1 probes the power spectrum at the resonance frequency, which is, say, 10 to the 8th, 10 to the 9th hertz, and T2 in the kilohertz to maybe 100 kilohertz range. So it really is the only probe I know of to look in those frequency ranges. And it turns out that for the kinds of systems many of us in this room are interested in, those frequency ranges are really very relevant. So the early studies were mostly focused on understanding structure. Let's call it static structure. And I don't want to talk terribly much about that. There were literally hundreds, perhaps thousands of papers on various kinds of materials. Lots of work on zeolites, lots of work on clays, lots of work on all kinds of minerals, technological operations, technological materials, geological materials. Just a couple of examples. So these are silicon-29 studies from a paper we wrote with Steve Altaner in 1988, where we used NMR trick of separating signal by its T1 relaxation rate. And these are spectra for a mixed-layered illite smectite. And by manganese exchanging the exchangeable sites, we're able to separately resolve signal from what we interpret to be the Smectite component from the signal that we interpret to be the illite component. And by curve fitting these spectra, this is 3 resonances. These are silicons with 0, 1, and 2 aluminums next to them. By curve fitting that and assuming Wallenstein's rule, all of that stuff, we get a composition for the Smectite layers and their percentage, composition for the illite layers and their percentage. And it turns out that the composition one backs out of this is within analytical error of the chemical analysis. And that's an example of how NMR can probe local structure, in this case the aluminosilicate part of this structure, in a way that no other method could. And the important point is that in this case, X-ray diffraction, we believe, underestimates the number of Smectite layers present in these materials. And Steve Altaner had a long story about McEwen crystallites and all of that. But the point is that NMR is a very effective probe of static aluminosilicate structure. Aluminum-27 was also a major topic, major probe in those early days. Just a couple of examples here. There's a synthetic illite Smectite. The important point here is that you can resolve, if you do it right quantitatively, the aluminum, 6-coordinate aluminum, 4-coordinate aluminum. And then here's some mogolites and aliphanes. We could collect a lot better spectra than these days. But again, looking at the ratio of 4-coordinate and 6-coordinate aluminum. NMR is also useful in looking at reaction progress and in characterizing amorphous phases. And there's a whole world of using these NMR methods to look at glass structure. But here there's a paper we did with Peter. Here's Hectorite. It's the so-called Q3 site there. React it with hydrochloric acid, and what happens? The Hectorite dissolves, precipitates hydrous amorphous silica. So there's the residual Hectorite, and that peak, and that peak are from the amorphous silica. That peak with silicons with no hydroxyl groups, 1 hydroxyl group, 2 hydroxyl groups. And there's actually very big literature in NMR just looking at amorphous silicas. But the point is that this is again methods for looking at reaction progress and quantitatively characterizing amorphous phases. All right. So we did a lot of work like that. But then, you start the whole periodic tables there. What about soluble species and fluids? What's going on there? Well, there's just a list of some of the nuclei that one can look at. The alkali cations, some of the alkaline earth cations, but also lots of anions. And we did a lot of work on anions and layered double hydroxides. I'm not going to talk about that much today. But these are species that at room temperature at least are mobile. So how can we deal with this? Also the fluid phases. You can look at water, hydrogen, deuterium, oxygen and water, carbon dioxide. I put methane there, but the interest these days in CO2 sequestration, enhanced oil recovery, all of that, methane standing in for the hydrocarbons, and many organic and biomolecules. These things are mobile at room temperature, and now the dynamics are likely to be important in understanding the NMR results. And that's where molecular modeling comes in. So what's the connection between NMR and molecular modeling? It turns out that the structural and dynamic information from NMR, just from the spectra, really are often difficult to interpret on a molecular scale in an unambiguous way. One can think of lots of, say, types of motion that might lead to the same results. So this molecular dynamics modeling, and we're going to have a whole session, a couple of sessions today on these computational molecular modeling techniques. Now, very, very mainstream stuff. But this particular technique, molecular dynamics, looks at structure, dynamics, and energetics through time. And it turns out you can make pretty close connections between the results of this MD modeling and the NMR results. Quantum chemical calculation methods can't model big enough systems. They can't look at the dynamics over a long enough time period. So MD is really the choice for how one tries to calculate dynamics related to NMR. And of course, you have to have empirical force fields, and that's where Clay FF came in. That's changed a lot of how we do things. And again, these techniques developed over the last, I don't know, whatever, 75 years or so. Now very well developed. Now what have I done? There. So the output, all kinds of structural information about the solids and the liquids, energetics, details of atomic motion, diffusion, lots of things that we'll be talking about through the day. So these were the first data that our group collected where I thought, gee, you know, I wish we could calculate what's going on. So this is a paper by Chuck Weiss, and here we're looking at cesium NMRs, or cesium-133 NMR spectra, for hectorite at 100% relative humidity. You equilibrate it, put it in the rotor, seal it, it stays there. So what are we looking at here? Here's, let's say right there, that's the more or less room temperature spectrum. A nice single narrow peak. This little peak over there is an impurity. Nice single narrow peak. Looks pretty straightforward. You have a single cesium environment in this clay. Makes kind of sense. But Chuck's in, not so fast. Let's look at low temperature results. So it turns out you got onto lower temperatures, and the peak's broadening there. And you get down here, and all of a sudden there's two peaks. Well, okay. What's happening is this classical NMR behavior, absolutely classical NMR behavior. Turns out there are, in fact, two different types of sites for cesium in this sample, one giving that resonance there and one that resonance there. With increasing temperature, the frequency with which the cesium is hopping between these two kinds of sites is increasing. And at temperature, where you're seeing both those resonances, that frequency is less than about a kilohertz or a tenth of a kilohertz or so. In this region here, where it's kind of blending together, the hopping frequency is kilohertz or thereabouts. And up here, where it's very narrowed up, the frequency is greater than 10 to the fourth hertz or so. So it's an example of why variable temperature work is important in understanding these kinds of spectra. And it turns out that the position of that peak is exactly the weighted average of the positions of those two peaks. So in 1990, we ended up assigning, as best we could, this peak here to something that we thought were inner sphere complexes, and that one to outer sphere complexes, tightly and less tightly held cesium atoms to the basal surface. So later on, Smith published a paper in 1998 that confirmed these results. He said that's what he found. Two kinds of environments for cesium, these inner sphere and outer sphere complexes. It's always scary when you make an interpretation and then somebody comes along and does a calculation. And says, is it right or not? So it turns out this was right. And more recently, Andre and one of his students has done a more advanced MD kind of calculation, that's pretty much shown the same results. So that got us really thinking, gee, maybe we need to connect in a more organized way the NMR and the computational modeling. So I spent some time with Randy at Sandia and learned a little bit about it. Andre came to Illinois in the early 1990s, and we've done a lot of work since then. So I want to look at a few examples of the kinds of things one might get. So here is sodium-23 NMR of our favorite hectorite. We use hectorite because it's very low iron. It's trioctahedral clay with lithium for magnesium substitution. Story here is very similar to what we had for cesium. And I want to look at what we're calling wet paste here. That's that spectrum down to that spectrum. Again, at high temperatures, narrow peaks, rapid dynamical averaging of what's going on, rapid dynamic averaging among various sites, and at low temperatures, finally broadening out. In this case, not resolving, at least at this temperature, two different types of sites, just a sort of range of sites. So in this wet paste, fluid phase is present, probably a lot of delamination of the clay layers. The sodium very mobile on the surface. Room temperature, very rapid exchange, decreasing rate of motion at low temperatures. So lots and lots of people have done MD calculations for sodium on smectites and other clays, pretty much always finding the same results. Here's some simulation cells from Oscar. So these simulation cells look like this. There's a box that in each of those things is an atom. This red over here are the water molecules. And you have this box full of atoms and force field among all of them. And then you replicate that box in 3 dimensions to take away artifacts of small systems. So you'll see today lots and lots of things that look like this that are snapshots out of a MD simulation. So in this case, we have clay layers over there, a water layer here with some solute in it, and there's another clay layer over there. So that surface there is that surface there. That's how these simulation cells go. Here we've taken the water out so you can see where the sodiums are. And the important point that this result shows, lots of other people's results have shown, is that on these smectite systems, sodium is associated with the surface as outer sphere complexes. That is, they retain their hydration shell, the water molecules, attracted up to the surface by Coulombic interactions and kind of are there, but they're also present out in the fluid. And then they're in, by NMR standards, very rapid exchange between these inner sphere, between these outer sphere sites and further out into the fluid. Diffusion coefficients of the order of 10 to the minus 6 centimeters squared per second. The point being that this exchange between these surface-associated outer sphere sites and sites further out in the fluid is fully consistent with the solution-like spectra that we get at room temperature, and that at lower temperatures, the rate of exchange between those sites decreases, and we're seeing those broader spectra, broader resonances. Oops. Okay. So there we are. All right. Now I want to look at this spectrum there, sodium spectrum of hectorite, held at 43% relative humidity, probably mostly a 2-water layer complex. That spectrum is very different than those, and believe it or not, that's a single NMR resonance. these quadrupolar interactions lead to really peculiar looking line shapes. And we'll see even more of them. But that is a single resonance that has quite high axial symmetry. You can extract symmetry information from these line shapes. And I want to look at what the NMR, what the MD has to say about those resonances. So this is from a paper by Kristen Morrow and a bunch of us in our group, published a couple years ago. Here's the simulation cell with a 2-water layer complex. What we see there is there's the clay layer there, layer of water molecules, and those blues are the sodiums. And in this 2-water layer complex, these sodiums are in a time average sense in very good octahedral coordination, 6 coordination by water molecules, and not directly coordinated, most of them not directly coordinated to the basal surface. So that's consistent with the observed time average quadrupolar NMR resonance, that funny looking quadrupolar line shape. So that's something we've always wanted to know. Is what's that sodium coordination really look like? Well, it turns out we can do more than that. And I want to switch now to deuterium NMR, now for the same samples that we had the sodium results for. So deuterium is really peculiar. It's quadrupolar, but it's got nuclear spin 1, so it's got you're observing 2 different resonances. And the line shapes are really funny looking. And I'll try to go through them here. So let's look at this one here. This is for a paste, bulk water present. Most of this resonance, let's say that and that peak and all the other associated stuff there, is actually ice. You take this stuff to minus 80 C, and the bulk water freezes up, and you observe this ice spectrum. But there's a small resonance there that's clearly not ice. Go to minus 50, and the dynamics are getting such that we can see better what's going on. There's still ice present, but then we have that split doublet there that represents deuterium in water molecules that are associated with the surface, what we call proximity-restricted water molecules. And with increasing temperature, the splitting between those doublets decrease until at room temperature it's a very narrow peak. However, it's still not completely narrowed. What this represents is water molecules associated with the surface that with increasing temperature become more and more mobile, below minus 30 or so. There's probably ice there and a thin water layer on the surface. And the narrowing represents increasing rate of motion, rate of exchange between surface-associated water molecules and bulk water molecules. But there's still this residual quadrupole splitting, indicating that over time, all water molecules, or time on the sort of kilohertz time scale, 100 kilohertz time scale, all water molecules are probing that surface. Okay. Story with the 43% humidity samples, mostly 2 water layers probably, is really quite different. There's no observable bulk water here, and we see this split peak like that. That's actually very similar to that split peak, but it doesn't change with changing temperature at all, except at very lowest temperatures where the frequency of exchanges is going down. What do we see? Well, there's this residual quadrupolar splitting. You can quantify that. In this sample, the water molecules are all doing their dynamical averaging. but the motion is not isotropic. This is interlayer water molecules. And this temperature independence is an NMR phenomenon. If the rate of motion is of the order of an order of magnitude faster than the line shape, then you just get a fully dynamically averaged spectrum, so-called fast limit. And that's what's going on. The rate of motion, whatever the motion is, of these water molecules is greater than the, let's call it the kilohertz range, 10 or 100 kilohertz, at all temperatures there. Okay. So, where does the computation come in here? A couple of things. First off, one of the great things about deuterium NMR is that you can calculate the line shapes for particular assumed types of motion. And people do this all the time. This is very highly developed in organic chemistry. People look at rotational frequencies of hydrogens on methyl groups and things like that. So, so Jeff looked at this and he says, he did calculations for the so-called tetrahedral jumps, which is what water molecules do in ice. Well, that doesn't give the right spectrum. He said, well, gee, maybe it's just water molecules doing rotation around their dipole axis. It would be like that. Calculate that. It doesn't work. And he said, well, maybe there's two kinds of motion. And it turns out the model that works is simultaneous rapid rotation around the dipole axis there, along with hopping of the water molecules among these sites with some average angle, omega, between the normal to the clay layer and the dipole vector. And that turns out to work really well. So this combined, what we call C2, C3 rotation simulates the spectrum really well. And it turns out this is the NMR line shape in this case is exquisitely sensitive to this angle omega. So these are calculated line shapes here, these from there down to there, for omega values in this fast limit C2, C3 rotation for different values of omega between 62 and 45. And you can see how that line shape changes. And it turns out these line shapes are symmetrical about the angle 54.7 degrees, which is the NMR magic angle, and also the octahedral angle. If omega was 54.7, the line shape would be as narrow as you would get with magic angle spinning. But it's not. It turns out that the best fit is either at 51 degrees or about 59 degrees up there. So it's that angle there we're looking at, and these deuterium data give us information about now the time. This isn't instantaneous, right? This is time average. All these molecules are moving around, and the deuterium spectra are looking at the time average value for this omega for those water molecules in the interlayer there. All right, that's good. So we went ahead and did MD calculations for this two-layer hydrate, and the molecular dynamics gives you all kinds of structural dynamical information. One of the things we could extract from those calculations was this average omega value, which turns out to be 51 to 53 degrees in that range. So the point being that the MD results lets us interpret this now as we can say that the omega value is 51, not 59, meaning that omega is relatively small, and that the octahedron of water molecules around the sodium, rather than being a time average perfect octahedron, is stretched a little bit like that. Being, in the qualitative, you can say it's being pulled by the clay layers. So again, the MD connecting directly to the NMR results to help us understand structure and dynamics. There are many other molecular scale computations one can do. There's a number of so-called accelerated methods, one of them being metadynamics, which is sort of MD, except that you define a particular reaction variable, particular reaction variable you're interested in, and computationally you force the system to go in the direction of that reaction variable. So this visiting scientist we had was Mirmatha Krishnan, did these calculations where did the metadynamics for this sodium hectorite system, looking at these various angles. And one of them is this what he called theta, which is sort of related to omega, except it's only for water molecules coordinated to the sodiums. So he's forcing theta to change and calculating the energy as a function of theta. And here are the results. Here's the results for a 2-water layer system. That's this one here. And he finds theta at with minima around 50 and the opposite of 120, which is better be that, because that's more or less the values we see for from the NMR. But the important point here is that this method now lets us calculate the activation barrier for the hopping of a water molecule from this layer to that layer. And going from that site there over the barrier to that site. And it turns out that's about 3.3 kilojoules per mole. And that's pretty low, easily accessible at room temperature. And you make some assumptions and you get a correlation time of about 0.4 picoseconds. So very consistent with the fast limit NMR model that we have, where we're probing kilohertz or say 100 kilohertz frequency range. So again, the NMR results and the computation results fitting together very, very well. All right, a couple of more minutes. I want to talk now about work that is incomplete, work we're involved with, but I think work that will be of great interest to this community. And that is in situ moderately high pressure and temperature NMR of under supercritical CO2 conditions. So our collaborators at the Pacific Northwest Lab, David Hoyt, a lot of other folks there, have developed this high pressure, the system for loading NMR rotors and maintaining high CO2 pressures. So they're funded to work on carbon sequestration. So you can now do these experiments with moderate CO2 present, supercritical conditions. In the case of the spectra I'll show here, temperature of 50 C and pressure of 90 bars CO2 under magic angle spinning conditions and just simple block decay, 1 pulse NMR experiments. Oops. Okay. So we looked at 2 samples, sodium hectorite, sample we've been talking about today, and a composite of sodium hectorite and Swanee River natural organic matter. The question is, does the presence of organic matter in these clays have an effect on the interaction of the clay, of CO2 with the clay? The answer, of course, is yes, it does. So these spectra here are the carbon NMR spectra obtained in situ for different things. There's a blank. That top one is the supercritical CO2 only. There's the sodium hectorite in the middle, and the red is the composite. Doesn't look very exciting, does it? Yeah. Turns out There's a slight increase in line width, but not very exciting. But the important point there is that under the conditions of our experiments, no carbonate species formed. Right? So there's water present in the clay. It was equilibrated at 43% humidity. There could have been reaction of the water with the CO2 to form carbonates, some carbonate species. None of those formed. So we're looking at CO2, the effects of CO2. We then looked at the sodium. Again, in situ observation of sodium, base hectorite, composite with and without CO2 present. For the base hectorite, what happens is that we don't see much change in line shape, but we do see increase in intensity. For the composite, we see, with and without CO2, both an increase in intensity and a change in line shape. So we interpret this to be reduced kind of average quadrupole coupling that would lead to increased signal intensity, and we would say that the CO2 in fact enters the interlayer galleries and affects the sodium NMR behavior. So how do we interpret this? Remember, these are early experiments. We're not certain how much water was retained in the interlayers. We're going to try to do those experiments this summer. But the point I'm trying to make is that there's lots of potential for systems that people in this room might be interested in to understand what's going on. So it also turns out that the presence of CO2 has a big effect on the sodium relaxation. It means that whatever mechanisms are going on, it's changing how the NMR, and this is T1 relaxation. So processes at say 10 to the 8th hertz are somehow affecting the relaxation. We always observe two components: a short relaxation component with T1 values of 2 to 20 milliseconds, and a long relaxation component with T1 values of 250 to over 1,000 milliseconds. Interpretation is a little controversial. One possibility is that the fast relaxation is 1-layer hydrate, slower relaxation is 2-layer hydrate. Again, not entirely certain how much water is in there. But two important points are clear. The presence of the organic matter decreases the relaxation rate. That's for both the short and the long component. The presence of CO2 increases the relaxation rate. So clearly, both the organic matter and the CO2 are having some kind of effect on the dynamics of what's going on, the water, CO2, sodium, clay interactions that are affecting the relaxation of the sodium. So we've done some NMR simulations. Oscar's done some NMR simulations. Again, here's a clay layer. Here's a fluid layer there and there. All this black stuff here is a model NOM molecule, the standard TMB molecule that a lot of people are using for these MD simulations involving organic matter. In this simulation, the fluid is entirely CO2. And what happens there is that this TMB model molecule has sort of hydrophilic components, carboxylic groups that in this simulation are deprotonated, some other hydroxyl groups, amine groups, and also hydrophobic areas, rings and chains. So what happens is that this molecule flips around. The hydrophilic components mostly go towards the surface, where the sodium bridges between, say, the carboxylic groups and the surface. The hydrophobic components are sticking out and are coordinated by the CO2. And what we would say is that this sort of locking down of the sodiums onto the surface actually increases the sodium relaxation rate, because it's counterintuitive, but that is the way it works, because it's increasing the intensity of the power spectrum at the lower Moore frequency. It's well understood phenomenon. And again, that's structure is actually comparable to the Sutton and Esposito structure for calcium monomerilonite with NOM. So what we're arguing tentatively is that the presence of the NOM sort of locks the sodium in and increases this relaxation rate. Simulations with both water and CO2 present with the NOM are kind of interesting. Here's the same system. There's the water, as everybody expected, goes to the surface. The CO2 is present in the center of the inner layer, not associated with the surface. And these NOM molecules sit not now on the surface, but at the interface between the water and the CO2. Again, with the hydrophilic components pointing toward the water, coordinated to sodiums, and the hydrophobic components out toward the CO2. And it looks like, though we still have more work to do, that the sodium associated with the NOM is actually more mobile than the sodiums associated with the surface. And so in time average sense, this increased mobility causes the decreasing relaxation rate for the sodium that we observe in the experiments. So this high pressure CO2 system is preliminary work, but we're pretty excited about it. We have more instrument time coming up this summer, and I do think this will be very useful tool for lots of things that those of us in the clay world are interested in. So just to make final couple concluding points, NMR, unique element-specific molecular scale structure dynamics, but often hard to interpret uniquely on the molecular scale. Computational molecular dynamics, other methods, very helpful in helping us interpret experimental results, understanding the structure, energetics, dynamics, helping develop hypotheses that can be tested experimentally, and are especially important for these mineral fluid systems where there is dynamics on the frequencies greater than kilohertz going on at room temperature, with variable temperature work letting us understand those processes in more detail at low temperature. Thank you very much for your attention. Again, thanks for coming. Thank you.